Shall I turn on my video? I'll turn on. So,
yeah.
Okay. Just a second. Okay. All right. Hello, everyone. So I'll talk about my recent work on this topic, exploring non-equilibrium dynamics in non-unitary quantum cell automata. So this is joint work with the CI professor Gavin Brennen and the PhD student Elizabeth. And this is, we are based in Macquarie Center for Quantum Engineering in Sydney. So I'll just start with very quickly with something that we all know, cell automata, that of course this cell automata framework has been used in complex systems for a long time to explore emergent dynamics. So cell automata just consist of grid of cells, and the cells can take on some states, typically binary states, either 0 or 1, and they undergo some dynamics. So they follow some rules, which are usually, they have to obey some locality constraints. So typically the rules are nearest neighbors. And from simple rules, we can get very complex dynamics. But this has been studied for a long time. But this framework can be extended into quantum domains. So, so quantum cell automata is a field in its own right as well. And the idea there is to replace this, to allow the states to be qubits. And the rules can be now locality and causality preserving quantum maps. So I'll be talking about this QCA framework. And this is really physically realizable in this state-of-the-art atomic physics experiment. For example, you can use Rydberg arrays, which can be controlled. This quantum systems can be precisely controlled using lasers. And I'm not gonna go into the details of this, but it's detailed in this paper. Essentially, one can realize controllably different unitary rotations, but also one can generate non-unitary dynamics. So that is to say, one can have controllable dissipations, which is neighbor dependent. So it's actually the dynamics the rules that we are dealing with are completely positive trace preserving maps rather than unitary dynamics. So the non-unitary extensions of quantum cell automata are much less studied, but it could be that they actually quite useful. For instance, it has been shown that one can use non-unitary quantum cell automata to robustly prepare entangled states. So yeah, there could be a way of preparing many body quantum states which are resilient to some kinds of environmental noise. So that's one application. But I'll be talking more on using this to study non-equilibrium phase transitions, so more fundamental studies. So we've been looking at a classic model in non-equilibrium statistical physics, directed percolation. So this is a famous spreading process. Typically, directed percolation is formulated as it is in the picture. So we have a lattice of sites which could be active or empty, and there is a flow of activity along the bonds joining the adjacent sites, which can be present or absent with probability P. So there is a transition as we vary the probability p. There is a transition from activity stopping, dissipating, or percolating to the end, to indefinitely, essentially. So this is the absorbent to percolating phase transition, and this is phase transition belongs in the famous directed percolation universality class. So this has been studied very extensively, but what is not yet very clear is what happens if we allow for some quantum correlations in this system. Does this correlation change the universality class? It's not entirely clear. So this is sort of the open question that we are trying to get to. And so we decided to try to construct a model of directed percolation which would allow for quantum fluctuations. And we started with a classical model, the Domany-Kinzel cell automaton. So this is a classical stochastic lattice model which exhibits directed percolation phase transition. It's essentially the rules are probabilistically update the state of a middle side if with probability x, if the neighbors are 0 and 0, with probability y, if the neighbors is 0, 1, 1, 0, and with probability 1, 1, with probability z, if the neighbors are 1, 1. And one can quite easily show that if y and x is equals to 0 and y and z equals to p, the dynamic is equivalent to side directed percolation. And if y is p and z equal p times 2 minus p is bond directed percolation. So this has been studied using various techniques like Monte Carlo simulations and so on, and one can map out the phase diagram of this. And in fact, this is often used to actually study the criticality computationally of directed percolation. But it's quite nice because it's block partitioned cell automata, and we need block partitioned cell automata to extend into quantum domain, right? Because essentially because of no cloning, we cannot store states. So a block partitioned update rules is essential. So we took this rule and we just start with a master equation, but we allow so the jump operators that act on the qubits, they essentially of the form of the Domany-Kinzel model. So the rates are chosen such that the transitions are neighbor dependent, and the rates are chosen appropriately, right? So then we wanted to simulate this and to see whether we can actually see directed percolation in this model. So notice that we can add a Hamiltonian term, but we can also set it to 0, making this completely dissipative model. So we simulated this, and just briefly on the simulation. So what we do is so it's an open quantum system. So states are density matrices, and we vectorize this. So essentially replace bras with cats. And then the rules are, so this is a matricized version of the Lindbladian. So this is exponentiated, and this gives me the completely positive maps, which are basically, I kind of partition this into blocks, and this is acting on the state flow. But here we can have actually two limits. We can either let tau, so this is the time for which the master equation acts on each step. You can either make it very small, or you can make it very large. So in the limit of very small, it's by trotterization, this is actually, you can think of it as the dynamics acting on the whole system at the same time. Or if it's very large, it's really a discrete dynamics, right? So, and we wanted to see if actually if we can see criticality in both of those cases. So I simulated this using infinite time-evolved block decimation, and yeah, I get the results like this. So this is using, you know, of course I have to truncate the bond dimension, but this bond dimension of 256, we, for instance, get this result. So this is for tau small. You can see that for small values of P, the number density essentially decays to 0. So this is in the absorbing phase, and for large, it stays constant. So this is percolating phase, and one can actually extract critical exponents of these transitions in a standard way, and it does seem to be corresponding to the site directed percolation. Although I have to repeat this and do this more carefully. This is sort of preliminary results. For tau large, we get similar thing, like the phase transition is in the right place at around 0.7, and the critical exponent is fairly consistent. So that was quite nice to know that you can use that actually you don't need block partitioning to realize this in the lab, that you can actually use a continuous dynamics and see direct percolation phase transition. So, and finally, we kind of still exploring and thinking about maybe constructing Hamiltonians from.
Just to say that 12 minutes are over now.
Okay, so. All right. I think I'm pretty much finished anyway, so I'll finish on this slide. Yeah, and take any questions.
Okay. So yes, so we have time for questions. That's very nice. Thank you for your talk, which was very interesting. So are there any questions? Maybe you can go out of the screen sharing for a moment, yes, so that we can better see who has a question. So you can use the hand tool, or you can also use just your microphone. You can switch on your microphone if you have a question. Do you know how to use the hand tool in Zoom?
Oh. I mean,
well, there seem not to be any question. So I have one question. I am doing a lot of simulations with a cellular automaton, but not in the quantum way. So just in the the normal deterministic way. So what should somebody like me get out of the talk? So what changes the cellular automaton when you introduce quantum fluctuations?
Well, for this particular problem, one thing is it's definitely harder to simulate. Yeah, it's even there is some very recent papers who are doing similar work to what I was presenting, and so far they didn't see that actually the directed percolation universality class didn't seem to be affected by the quantum correlation, which is surprising because for contact process, like the quantum version of contact process,
yeah,
it did change the universality class. But for Domany-Kinzel, model and directed percolation, it didn't. But nevertheless, the simulation was much harder to do. Like if you do the matrix product state sort of the version or like DMRG or anything like that, then the bond dimensions are much larger than for classical statistical mechanics. So it's still not really clear. How can we actually harness this quantum correlations in some way or not? But so far it's only apparent that it makes the simulations more difficult. But we're trying to come up with some applications for what's and trying to understand what it is. Yeah.
So did I understand it correctly that sometimes the classical results are maintained when you do a quantum?
Yeah, that seemed to be the case for some. Yeah, for this particular model, but yeah, in a sense, the critical exponents right at the criticality, right? But that is a surprising results. People don't really they didn't expect to see that, so we're trying to understand this.
Yeah. Okay. Thank you. Is there any other question? No. Well, then I would like to thank you again for the talk. And so let's go to the next talk by Xun Li. Could we check everything? So Xun Li, can you say something? Hello, Xun Li, do you hear me? Oh, actually, I see Xun Li is not here. It's not in the list of participants. So I would suggest we check later that Xun Li has arrived, and then let's go to the next talk by Rico Berner. Is Rico here?
Yes.
Ah, okay.
Indeed, I'm here.
Yeah, that's a relief. That's a real relief. Yeah, sorry for that. I hope nobody will miss your talk because we shifted it. So that is always not...
Can you hear me?
Yeah.
We have to wait for the time.
Yeah, we do.
Minutes
Okay.
from now.
Okay.
Okay.
We have to start his speech at his time.
Yeah, okay. I agree, because somebody might have scheduled your talk and then might miss it, which would not be good.
Alrighty.
So it's really a pity that Xun Li is not here.
Yeah, but we might check that the technique works, right? So I can just
yeah, of course, yeah, we can do
it. Just to share my screen. Works.
Yeah, works perfectly.
Just let's see how it works when I start at the beginning. Okay, everything's fine.
Yeah, looks excellent. Okay. Yeah.
Great. Then it works. Now we can wait. So it's supposed to start at 5 past, right?
Yeah, exactly. Yeah.
Scheduled like this. Okay, perfect. So see you in a minute, like a few.
Yeah, okay. I think I would like to welcome everybody back. And okay, so now it's a pleasure to have Rico Berner here. He will speak about what adaptive neural networks teach us about power grids.
All right. Yes, so thank you very much. Yeah, thanks to all of you. Yes, I would like to talk about actually what we can learn from adaptive neural networks for the treatment of power grid networks. And this is joint work which I have done together with Serhiy Yanchuk and Eckehard Schöll, and we are from the TU Berlin in Germany. I would like to guide you through three main points. So in the first part, I would like just to show you what do we mean when we talk about adaptive networks and power grid networks, like on a model base. In the second point, I would just formally tell you what is the bridge between an adaptive networks and power grids and how do they relate. And having this bridge, in the third part, I would like to show you what we can learn from adaptive networks actually for power grid networks. Okay, let us start. In the beginning, I would like to talk about adaptive networks. And when I talk about adaptive networks, I have some neuroscientific context in mind. So I consider each part of a network, each node on a network as an individual neuron. And it has been found that there is actually a mechanism in neuronal circuits that can lead an adaptive network structure. So a change in the coupling weight, which is given by, like the coupling is usually given by synapses, and the weight of each synapse can be adaptive to the actual state of the neurons. So consider two neurons, which are like temporal, they're tonically spiking, so they have some spiking times here. And experiments have shown that according to this rate, so to the spiking times, the weight between two neurons can change. So there are certain adaptation rules, we call them. But from the model point of view, I would like to go back to more simplistic models. And what we are considering in our, like for the rest of the talk, are phase oscillator models. So here in the phase oscillator model, each neuron or each oscillator is just given by a one-dimensional variable, which is the phase, can be represented on the unit circle as a value of 0 to 2 pi. And in our model, we have the natural frequencies for all the phase oscillators. We have a coupling function f that just determines how they interact. Then we have the adjacency matrix, or the entries of the adjacency matrix, which gives us just the base topology. And we have the coupling weights. And the coupling weights, as I said, they are adapting on the actual state of the phase oscillators. So we have included in the model in linear decaying part and an adaptation function G, which depends on the state of the individual oscillators. So this is what, when I talk today about adaptive networks, this is what I'm going to talk about. The second thing, power grid networks. Power grid networks, for instance, here on the right-hand side, they are just, I just show you the generators and consumers in the German ultra-high voltage power grid networks, for instance. And here, usually, like dynamically, you're looking for synchronous solutions. So if you want to provide robust power supply, you're looking for synchronous solution and stable synchronous solution. There are also other questions for power grids that have been addressed also by using dynamical models like cost efficiency or dealing with decentralized network structures as they show up in modern power grid networks. And to model the dynamics in such a network, again, phase oscillators has been used widely to understand it. And here, the phase oscillator are described by a second order differential equation, which is called the phase oscillator model with inertia. And the dynamical variable, in fact, are phi, again, the phase, and the angular velocity of each oscillators. Here, the adaptivity, like the network structure is not adaptive, but given by adjacency matrix. And we have of course, we have a coupling between the oscillators, which is given by a coupling function. The power that is injected in each oscillator or each rotor in this power grid network is given by this value pi. All right, so we have two phase oscillator models, one for the adaptive networks and one for the power grid networks. The next question is, do they relate and what do they have in common? And it has been shown that like from dynamical point of view, there are a lot of effects that they have in common. And to see why this is the case, we just look again at on the left-hand side of the power grids model and on the right-hand side, the adaptive network model. The power grid model, the second order differential equation, I just rewritten in the first in the set of first order differential equations. To make the right-hand side more similar to the left-hand side, we say, okay, we restrict our adaptive networks to the subclass of f equals to 1, and we put epsilon to gamma over m, just to make it more like similar. And then we can say, if we introduce new variables and say what we call them pseudo coupling weights, we introduce new variables, then we can rewrite the left-hand side to the right-hand side. Yes, it is not, the choice for this equation is not unique, but it can be done. We can like motivate the choice by physical reasons. We can say that these ij's are the power flows on each line. In fact, we can show that these two equations are actually dynamically equivalent. So actually, the thing is that we have to show that the dynamics of this model, which is higher dimensional because it has a lot more variables, is restricted to a lower dimensional system. It can be done. So and the dynamics, of course, on the lower dimensional system is governed by the equation of the left-hand side. And it can be done, and we have written it up, but I spare you the details. We have written it up in this manuscript. Finally, we arrive at we can translate notions from the power grid now to the adaptive network. So on the left-hand side, we have the angles of the ith mechanical rotor given by the phase. And on the right-hand side, we have just the phase of a spiking neuron. On the left-hand side, we have the angular velocities of the ith rotor angle, so of the generator or consumer. On the right-hand side, this would mean that this is the total synaptic weight for each neuron. On the left-hand side, the pseudo coupling weight, which we introduced, is just the power flow from rotor J to rotor I. And on the right-hand side, of course, is the synaptic coupling weight between the neurons. All right, what can we learn? So I would like to show you now what we can learn from adaptive networks for power grids. It has been also like power grid networks or adaptive or phase oscillator models with inertia have been analyzed a lot, and so-called multi-clusters has been found. For instance, I would just to give you an intuition what multi-cluster states are. Here on the right-hand side, we see in the first column, it's the average frequency for each oscillator. In the second column, we have a snapshot, so it's, the phases at a certain point in time, if we run a simulation for the dynamical system. And here we have, in the third row, we have the corresponding pseudo coupling weights, coupling weighted matrix, where the weights are given in the color code here. And the thing is that starting from random initial condition and for certain parameters, we find that the whole group, that the whole network splits up into groups of oscillators with the same frequency, and all the groups are in phase synchronized. And this has been, like in the first column here, this has been found already. Using our pre-knowledge what we had on adaptive networks, so we studied a lot of phase oscillators on adaptive networks, we were able to find a new type of such multi-cluster states, which is the mixed multi-cluster states. In fact, it is the case. So we have here in the second column actually two groups of oscillators with different frequencies. There's one group, they're rather in phase sync, so there's just temporal shifts. And a second group, which is where the oscillators are splayed around the unit circle. Actually, this is two twisted states, some people would call it. And this is a new type which we found by using some some intuition and also some rigorous methods from which we can also describe by rigorous methods from the adaptive network case. Also, multi-cluster states and as they called here, a solitary state, also emerge in real power grid networks. I just show you one example. When you start from random initial condition and use the German power grid network, you can find situations where in the transition between coherence and incoherence, when you decrease the coupling between the oscillators, you find the emergence of so-called solitary state, because they are solitary nodes that decouple from the system effectively. So you see that the average dynamical frequency of each oscillator is almost the same as the natural frequency. This means that the sum here almost vanishes, so they effectively decouple from the network. And this has been analyzed or has been found already by Taha, Olmi, and Schöll, or by Hellman. And these states are very interesting because they are almost synchronized, and we would like to, and they emerge in the transition from incoherence to coherence, and we would like to control them rather to just turn down the whole network in order to achieve full synchronization, which we want to have in a accurately working power grid network. The new variables we introduced were the power flows, and they give some insights into the network, the dynamics of the network. Here you see again the same network structure, but now the average flow on each line. So the average of each of this in the presence of the solitary states, here where the solitary states are given here as the red squares, and you see that in the average flow is not very interesting. So there's no special thing about the solitary states. Here I just show that a large average flow is a dark line. A small average flow is a light line here. But if you look at the temporal variations of the flow.
Yeah, 12 minutes are over. But
okay, I will come to an end. It's just my last slide before later. Thank you. Well, if you look at the temporal flow ranges, then it can be seen how the variations of the flow spread out over the power grid network, and we propose that these new variables can be used now at a dynamical point of view, can be used to analyze and to control power grids and networks better. All right, to come to an end, I would just leave you with 3 concluding messages. First, we found the bridge between power grid networks and adaptive networks. We've shown that multi-clusters and solitary states exist and give some like new tools from adaptive networks to analyze these states. And we also analyzed in this manuscript the other way around, where we discussed the dynamical cascading of lines, which have been found for power grid networks, for adaptive networks, where it can be understood as an interplay of spike timing and short-term synaptic plasticity. Thank you for your attention, and I'm very happy to take your questions.
Yeah, okay. Thank you very much, Rico, for the nice talk. And are there any questions? Could you stop screen sharing for
a second? Sure.
Okay, so.
Hi, I'm Sneha.
Hi.
Very nice talk, and it's actually really interesting to see how you relate the 2 networks, because I've been working on them separately. It didn't occur to me that you can sort of have a same framework. So
yes.
I had a couple of questions. My first question is, did you is there any particular model in the context of neuronal networks that you took? Like, for example, FHN model or HR neurons. Did you test with any particular model, or?
So like this relation works very very well for this phase oscillator models, and this is where we have the formulas and all the analytics. We know that phase oscillators, like our phase oscillator model for adaptive networks, work very well to understand the clustering so the multi-clusters, for instance, in adaptive networks, and we tested it also for Hodgkin-Huxley systems as well, with some kind of spike time-dependent plasticity. But yes, but this is also like, this is only for the phase oscillator model. So the phase oscillator model works for, with like the phase oscillator on adaptive network works for neuronal models with like time-dependent plasticity. The phase oscillator models with inertia work fine for like short-time behavior in power grid networks. So there's the relation, but others, like mathematically, it's not possible to achieve.
I see. My other question was related to the splay states that you mentioned.
Yes.
So for generating those, did you start with random initial conditions, or was there a particular sort of like, for example, 2 pi by n or equally spaced initial conditions that you took?
No. This were by from random initial conditions. Yes. Otherwise, it would be just cheating, I would say. Yes. So this is random initial conditions. So there is a, let's say, non-measure zero basin of attraction.
Thank you. Really nice talk.
Thank you.
Yeah. Are there any other questions? Well, actually, I have a question about the equivalence of the two networks you
Sure.
have shown. If you would, so I think in this relation you showed us you had an algebraic relations between the parameters in the two systems.
Yes.
So if you would look at that from a, let's say, parameter fitting point of view, would you, if you fit one to the other with less or more parameters, would you actually get the correct values, something like that, because the dynamics is equivalent?
Oh, that's a good question. I've never looked at this equation like this. So actually by parameters, you mean fixed values, right?
Yeah, and then you vary them in order to get so that the dynamics is exactly the same.
So what we could do.
So you would take the data of one of the networks, the output, yes, as input to the other one, and then in a learning kind of way.
Yeah. Yes, your point. Yeah. So like from the dynamical point of view, at least if you restrict yourself to the adaptive, like to simple subclass of adaptive networks, I mean there should be no difference because they are one-to-one.
Exactly.
I would also, like from our other studies, which we like where we studied the other direction, so having something on power grids and going back to study the adaptive network, I would say you might be successful if you try to find some parameters that fit the model. Yeah, but so it might be possible also for the larger class of adaptive models to come somehow to mimic the dynamics of a power grid network. Yes.
Yeah, because that is what you would expect from a well-functional neural network, that it can learn from the data and then exactly predict the dynamic. That was the background to my question.
Okay, I see. Yes, but we didn't. That's a great question, but we did not. Analyze this in detail so far.
That would be an interesting thing to do.
Yeah, I guess so.
Yeah.
Very nice. Thank you.
So, are there any other questions? Well, if not, then I would like to thank all the speakers again from today. We had only two, but nevertheless, it was two very nice talks. And I like to thank all the participants as well. And yeah, enjoy the conference further.
Thank you very much also for sharing.
Yeah. Okay, bye.
Bye.